And the more we can get harder problems, more complex problems, messier problems, earlier on in education, the better our students will be equipped for real life, for the actual problems they're going to be trying to solve. We are soaking huge amounts of confidence out of many students because they're told basically they've got to be good at this particular thing of calculating. And yet the skill of calculating is almost completely absent in what we actually need in the real world. I think we're going to see a very different set of people who emerge as good creative computational thinkers, and actually a broader set of people.
Hello and welcome to the Teens in AI podcast, where we interview leading figures in the world of AI from the perspective of young people. My name is Kate and I'm your host for today's episode, where we're talking to Conrad Wolfram, author of The Maths Fix, which argues that today's maths education isn't working to elevate society with modern computation, data science and AI. We hope you enjoy. It's so great to have you on the podcast today. Thank you so much for joining us.
Great to be here.
So Conrad is the co-founder and CEO of Wolfram Research, which is a huge organization with, I think it's fair to say, many different offshoots. So I was wondering whether we could just begin by you giving us an overview of Wolfram Research, what you do as CEO and what the organization does.
So we were actually founded by my brother in the US about it's a long time ago now, 1988, amazingly, was when Mathematica first came out, 23rd of June, 1988. And funny enough, actually, I discovered recently that 23rd of June was also Alan Turing's birthday as well. Our aim really is to push the envelope of what computation can do to help people. We believe in the power of computation to make the world better by allowing people to make better decisions. And we've spent a long time trying to build technology to help that to happen. And to start with, that was pretty specialist. So back in 1988, that was folks doing integrals, mostly sort of high-powered research people. Nowadays, partly through our efforts and other people's, and partly through the way the world's moved, computation is very central in what everybody does, whether it's data science or modeling. And we're in the middle of a pandemic where these things have been absolutely center stage. And so it's become sort of what we do at Wolfram is more universally to push any kind of technology that can help this through many, many other rungs of society. So in 2009, we launched Wolfram Alpha. And hopefully many people listening to this have used that for their homework and for other reasons. And in a sense, Wolfram Alpha is a way to sort of democratize this computation. So you can immediately interface with all the sort of computation you might want to do in a sort of drive-by way. And the other end of what we've done is to build Wolfram Language, which is a high-level programming, or what we call a computation language, to distinguish it from traditional programming, where we've kind of got all the computation built in. So you can immediately do high-level AI, high-level image processing just with a single command, and you sort of interfacing at a very high level, much higher level, we think, than things like Python. So those are the elements we sort of tried to bring together. Oh, another element is what we call notebooks. Those are familiar to some other folks have started using those now as well, but we introduced notebooks back in, I think, 89 as a way to be able to organize technical ideas. And so again, there are Wolfram notebooks which allow you to have interactive stuff around things. So anything to push the boundaries of computation, that's sort of what we do. And we have people around everywhere, really, based in the US. I'm based here in the UK. And we have really been pushing this envelope, and it's sort of like there always seems more to do than there was before. So it's not like we're losing anything now. So anyway, that's the very potted history of the last few decades.
So are there any places today where Wolfram technology is being implemented that you find particularly exciting, or that maybe you wouldn't have seen it being implemented 30 years ago?
That's a really interesting question. To deploy computational ideas on messy stuff needs higher powered computation. Health is sort of the example right now in my mind where it's sort of this on the cusp of being fully computational. where it's been so messy. You've got people involved, right? They're messy, not as simple as computers. And so you have a lot of messy data, a lot of complex data. You have huge numbers of data points, models that are multifaceted in all sorts of ways. And so in a sense, that's an area where the highest power is needed, and therefore it's taken the biggest computers and the more sophisticated software, our development over many years, etc., for that really to come of age. At the moment, you've got this thing where you go to the doctor with something wrong with you, and they say, well, I'm going to bucket this in this disease, and then for this disease I'm going to look up on a chart, I should treat you with this particular medicine. If you think about it, the bucketing shouldn't completely be necessary. What you really want is some parameterization of you. Now, I'm of this size, I'm of this weight, I've got these characteristics, et cetera, et cetera, et cetera, this genetics potentially. And then you're saying, well, I've got these problems. And then there's some basically computation to work out what the best treatment known is for that. I mean, that's where you'd like to be, but we're ways off that at the moment. And so I suppose that's a real push area that I think we'll see coming through.
And one of the areas that Wolfram is doing lots of work in is multiparadigm data science. And could you tell us a little bit more about what that is and how it differs from traditional data science, and actually perhaps how that would also impact the health industry?
So I'll say multi-paradigm everything, and data science is, you're quite right, that's a very central thing we've been working on. One of the problems is that there are many, many techniques for many areas of computation. And what tends to happen is people tend to pick the technique first and then figure out what the problem is one way to put it. What you need to be doing is take the problem and say, okay, we can deploy all these different techniques to figure out the best answer, to make the best decision, all these different paradigms of approaching the problem. And we'll just deploy whatever's best, or combinations of that. And that's the multi-paradigm approach. So one mistake here I often hear, for example, is when people say, I'm doing AI and that's machine learning. Well, machine learning is one possible technique, and there's several types of machine learning, but there's one set of techniques there, which you could broadly call machine learning, to enable artificial intelligence. But there are others, and we shouldn't confuse the mechanism with the objective in a sense. A lot of what's happening in data science at the moment is people are taking the techniques they used before and called probability and statistics and things, and they're calling them data science, but actually the same techniques. Or they're taking machine learning as the only approach and calling that data science. So what we're saying is take all the possible techniques that you could imagine, all the paradigms, and apply them to the problem. And then see, and sometimes multiple times, I mean, you might try several techniques and see whether you get similar answers so that you can get a much richer solution set. And so that's just generally our approach. You should implement, that's what we've done with Mathematica and Wolfram Language, you should implement as many algorithms as possible, put them in a container that's sort of self-consistent, so you can always deploy any of them. And then you should pick which ones to deploy or try multiple ones and see what the answers are. And I think what we're seeing is, with data science, the analyses are still, in many cases, extremely simplistic and quite bad. So people are, and a typical mistake is that people are taking, they knew about normal distributions, so they decided they'll deploy a normal distribution to figure out what to do with a bunch of data. Why are they doing that? Well, because they kind of knew about it from school, and because the normal distribution was derived from a time when you wanted to throw out most of the data so you could work with it. And so there are all sorts of problems like that that are forcing people. And in fact, we come on to this later. I even wrote a blog post about the exam fiasco last year in the UK with Ofqual and the like, who, in my view, deployed really substandard data analysis to figure out how to grade people when they weren't taking the exams. And I think there were many, many mistakes made in how that was done. And that was really this sort of thing. There wasn't a multi-paradigm approach where they took lots of approaches. They just took one thing at once. And that's usually not going to work with messy data like we're talking about.
Very much. As someone who was messed over by the algorithm, I completely agree. So as we come up with more and more ways to address a problem, and we can come at it from so many, as you said, different angles, AI will obviously be more incorporated into everything, even more than it is now. So what will our role look like as humans? Do you think that the creative element of innovation will always require human input?
It's always hard to say always, but yes. I mean, I think that is the value added area of what humans do. I mean, it's funny, as you look through different industrial revolutions, and I consider us being in them, some people call it the third industrial revolution, but I tend to call it the AI age we're entering. In a sense, the successful human is one that steps up to the next level. I think the next level when you've got AI is sort of this computational knowledge where it's kind of like you're interacting, you're managing AIs. You're the creative senior management in the team with the AI, in a sense, and you're figuring out what to do with it, and also not get fooled by it. Important part of management. You want to get you don't want it to produce garbage that you then accept as correct. So that's important too. You have to be skeptical. So I think very much creativity, knowing how to ask the right question, knowing how to frame the problem correctly, knowing how to interpret the results are critical elements. I think, knowing how to pretend to be the AI and do what it does, but sort of less well, doing the calculation in the middle of it is typically much less important and will continue to be so. And similarly, knowing, it's complicated. The issue about what you need to know, knowledge, there's always this big debate in education. How much do you need to know? Should you learn off by heart all sorts of things, or should you just should you just not have to learn any facts at all, and somehow you can work everything out? I think the truth is somewhere in between those, but it's like you have to learn knowledge, but different sorts of knowledge. You can't just know nothing, so to speak, but not necessarily, knowing by rote all sorts of algorithms effectively that you're never going to apply doesn't seem very useful either.
And as we do embrace the AI age, there's a lot of emphasis, therefore, on the need to teach soft skills and critical thinking as automation increases. So how do you expect this development to affect the job market?
There are several parts of this. So if you go back, I don't know, early 19th century, there was a movement to say, actually, most people need to learn how to read and write. And there were a bunch of people who said, that's crazy. Only the sort of aristocrats and high priests and those sorts of people need to learn that. And the rest of the population are, too stupid, not necessary for them to know it, kind of thing. But as you know, obviously, mass literacy became a big issue in education. And we now have a thing where, it really is kind of considered a human right by the UN and others. It's like everybody should learn to read and write. And I think it's clearly a huge success of education that most people can read and write. It's pushed society up to another level. And you really can't function unless you can read and write. I think computational literacy is in for a similar direction. So you need a base level of understanding of, how the data science work, what it means to interact with an AI, to some extent through language that it speaks. The things that, cause and correlation, issues that you wouldn't necessarily consider to be sort of dead center at the moment in education, but which I think will become almost like a human right to know. So that's one sort of edge of it. Now, you asked particularly about sort of so-called soft skills. I mean, it's funny because some of those I think of as questioning people or computers correctly, to be skeptical. Some of those are purely reading the room, reading how you're, but again, it's funny because I think of that as a problem with computers. When my computer just went wrong before we started recording this, there was, a bunch of diagnosis I was thinking of to do with my computer. Well, I do diagnosis with people as well. It's like a person comes to me and says, I'm unhappy about this. And I try and work out what the root cause of the unhappiness is, just like root cause of my computer going wrong, et cetera, et cetera. So I feel like these skills are very much, you can think of these in actually a very computational way, a computational process way. And we might get onto that process a bit later.
I think it's very much fair to say that perhaps the maths teaching of today doesn't fit the real world that you then enter into? I think, in my experience, probably one of the most used phrases in a maths classroom after I've forgotten my calculator is, when do I use this in real life? So are there particular stages if I had a computational thinking based math lesson, as opposed to the maths lessons I used to have where I was really trying to tick off the syllabus of the GCSE spec?
Oh, absolutely. And as you know, I just wrote this book, The Maths Fix, to specifically try and lay out what the problem is, how we solve it, and some of the politics around making a change so major in what's considered one of the key pieces, sort of pillars of our education now, which is maths, as you say. Probably the easiest way to think about this is I typically describe maths or computation as sort of a 4-step process. So you start by defining the problem. Actually, when I'm giving talks, I would often start by saying, if we lock everything down, turn off the air conditioning, there's no airflow in the room, and I talk for too long, how long will we survive? Right, so I'd have to rather overdo how long I talk for, even by my standards. So that's the definitional stage. That's stage 1. Stage 2 is you're trying to abstract this to maths. So traditionally, squiggly things you write on paper, in the modern world, code for a computer. And the point of the abstraction is really this. One of the biggest achievements of this problem-solving process is basically that you can take completely disparate things, whether it's an air in a lecture room, or whether it's how trees grow or something, and you can potentially put them into a relatively small number of formulations that we then have hundreds of years of experience, in some cases, of how to calculate an answer from. They're very specific. It allows you to be very specific. And that's, in a sense, the maths formulation that we're, to some extent, used to at school, and we can now do with code. So that's step 2, get it in an abstract thing ready for calculation. And step 3 is the calculating step. Take it from the question you set up to the answer you want. And step 4 is interpreting it and verifying it. So, okay, x equals 3. Was that 3 hours? Does that make sense? If it came out as -2, there's almost certainly a problem. But maybe 3 doesn't make sense. Do I believe that answer? If I go back to the original question, does that seem like the right answer to the question? How else could I verify this, etc.? And maybe I need to go around these 4 steps again to get a more specific answer, or try a different algorithm, try a different formulation. So that's, roughly speaking, the 4-step computational process. And what we ought to be doing in school is focusing on particularly steps 1, 2, and 4, getting a computer mostly to do step 3, because that's what happens in real life. What's actually happening in maths education is we are getting people, our students, to do step 3 almost universally. You're allowed a calculator sometimes, which, by the way, is out-of-date machinery. I mean, you use the current machinery you'd actually use in the real world. Nobody uses calculators anymore. That's just in education. Don't be 20 years behind. Use a computer with modern software. A computer could be a smartphone or something, but use something you'd actually use. And now that actually changes things more than you might think. One of the problems is, at the moment, that we're forcing students to learn a very small number of techniques, only the techniques that are amenable to them doing hand calculating with them. So I mentioned earlier the normal distribution. One of the reasons we teach normal distribution is because you can do it by hand. But actually, in mathematics, for example, there are, I think, 150 built-in distributions. So there's a question of why you would use that one. And actually, you typically don't want distributions anyway. If you've got millions of data points, you don't need to throw away the data points anymore, because the computer can handle them. So we're actually forcing students into the wrong techniques often, not enough of them, not learning how to handle problems where you can't do the calculating yourself. So then they make all sorts of mistakes afterwards, and we get horrendous problems. I would even say some of the financial crash of 2008, there are some elements of that you can say could be traced back to educational failures because people weren't using computers. So that's a rough guide to some of the things that I think are wrong with the process. And the more we can get harder problems, more complex problems, messier problems, earlier on in education, the better our students will be equipped for real life, for the actual problems they're going to be trying to solve.
And it's like some people drop out of maths, not because they're bad problem solvers, but actually because they can't do the calculations, so to speak. And I dread to think about those problem solvers who have actually slipped through the net because they thought they were bad at maths. I think of the people who are good at maths as the ones who got the top marks in the written exams, and indeed they are good at maths. But how might the definition of someone who is good at maths therefore change? What do you think it means to be good at maths today, and what will it mean in the future? What should it mean?
Yeah, there's an excellent question, and you're 100% right. So I think that, it's really bad. We are soaking huge amounts of confidence out of many students because they're told basically they've got to be good at this particular thing of calculating. And it's kind of not necessarily the be all and end all of their existence, but it's like maths is so important. It's so measurable in the exams. So you can immediately tell, it's slightly harder to judge whether your English essay is good, but maths exam, it's right or wrong, yes or no. You either did it well or not. And yet the skill of calculating is almost completely absent in what we actually need in the real world. And so, as you say, it's pretty much a disconnected skill from many of the others that surround computation. The computational thinking that I'm talking about is a far more creative process that involves understanding this step 2 of abstraction. Step 2 of abstraction is a very hard step to do, and it involves understanding all sorts of things about what you're abstracting from, about the context. If you don't understand the context well, you're likely to do a bad abstraction, because the abstraction relies on you knowing what's important, because you got some question you're trying to answer, and the question you're trying to answer, you want some answer to make some decision. In the end, the decision is going to have some human effect. Otherwise, why are you taking it? At some end of the tree, there might be lots of computers in between. There's a human effect decision. That's what we're trying to achieve. And therefore, understanding the context, understanding what's important in that context is pretty critical to the whole thing. And also critical to building up judgment of, where mistakes are going to happen, where interpretations are going to be wrong. So I think we're going to see a very different set of people who emerge as good creative computational thinkers, and actually a broader set of people. At the moment, we have a few people who do tremendously well at the existing maths, and that's great. If they enjoy maths, that's wonderful. I'm not knocking that. It's funny because what you want is some sort of mixture of creativity and applying process. So like if you, and this actually is true, I was thinking about this a lot, I talk about this in my book quite a bit. Many walks of life have this funny mixture. If you're in the military, you learn a lot of process, but actually the most sort of top-end military has to do a lot of creative thinking around the process to get to win. True of being an airline pilot as well. You have processes, but then when things go wrong, you've got to actually think around the process. It's not just a matter of being completely dogmatic on the process. Even being a scientist, there's sort of more creativity per unit process often, but there's absolutely process to go through to figure out what's going on. And even being an artist, maybe less explicit. So there's always this funny interplay, but the most successful ends, facets of society between process and creativity. And what I'm really suggesting is we have this computational process that people are not getting to grips with modern machinery of computers, and they should be able to deploy this to a wide range of what's done in their lives. But they don't even get the chance to do that because at school, what they're doing is just focusing on step 3, calculating by hand. They never get any context much around it. They're given toy problems, snooker balls or whatever it is that's easy for hand calculating, which nobody cares about. And they're not given problems that might relate to their lives, which tend to be messy. So they tend to need a computer to calculate them. And so none of this joins up. And as you say, people end up saying, why the hell am I doing this? I have no idea. It seems nothing to do with my life. And they're right in most cases. One question I love asking ministers in different countries around the world is, including some of ours here, is when was the last time you used a quadratic equation?
It's been a while.
Yeah, if they're quick off the mark, they say, to help my children do their maths homework.
Just not the point. I think it's so much that very early on in schools, and it's so dangerous, you tell a young person, okay, you're a creative one, or you're so good at maths, or science is your thing, and it just shuts people down so that they don't think that they're capable of multiple different realms of thinking, so to speak. And in your TED talk, you said that in an average day, I think we spend as a society is 106 average lifetimes teaching maths by hand, which feels like a lot of time lost. But when I think of early learning maths, I do think of mini whiteboards and building blocks and trying to figure out and understand conceptually what maths actually is. So how much maths would you have people learn by hand before we let automation take over? Is there any need to start with building blocks, or would you just introduce computing and coding simultaneously?
Yeah, that's a great question, and we don't have a full answer to this question. Here's what I would say. There are really two reasons for learning the hand calculating. One is because you actually use it in real life still. So I estimate things in my head quite often. Could I put them on a calculator? Yeah, I could, or a computer. People ask me, should I spend this on this, for example? And I do a quick multiplication in my head. And the real crucial thing there is to know how to set that up. But it is useful to have a feeling for it. Much more important, though, is to have a mental picture of different facets of what you're doing. What is a third of this chocolate cake is a sort of important picture to have in your mind. But multiplying, a seventh by a 20, by a 23rd, 1/7 by 3/23 or something, knowing how to do that technique seems pretty irrelevant to me. I've never had to do it. So it's quite hard to separate out some of the sort of basic maths that you need, which I think is correct. So I think early primary maths in many jurisdictions isn't too bad. It's a bunch of stuff you need, though I think the emphasis is slightly wrong sometimes. By the time it gets to sort of late primary and quadratics, it's gone completely off course into sort of the details of the mechanics without focusing on any of the concepts that you might have picked up. I mean, there is a second reason, which I've sort of touched on, which is sometimes when you do something by hand first, it helps you to get to grips with what it really is internally, so to speak, what's going on. Sometimes, but I think we've got to be very, very careful of this, because I think a lot is overclaimed for this in maths education. So, for example, people say, well, you need to learn long division because somehow that tells you about, factorization of various sorts and so forth. Well, it's kind of like most people who learn it by rote. It isn't something they use, doesn't seem very useful. Now, you might say, though, for equation solving, the idea of an equation is a useful abstraction. If you actually see that, x plus 2 equals 4, and if you subtract 2 from both sides, you end up with x equals 2, to see that the idea is a balancing equation, that might be somewhat useful to assessing the interpretation. So there are some cases like that, but I think they're fairly minimal. And the mistake often made by curriculum authorities and things is to think that if somehow you use a computer, you need to know how the computer works. You can't. I mean, I'm using computer now. I haven't got the foggiest idea how it works. I have more idea than some people. I know there are various levels. There's machine code. There are chips that have transistors in and things like that. But in the end, I haven't got the foggiest idea how it works. You can't predicate use of machinery on knowing how the machinery works. That's just not how the world moves forward. And that's as true for using computation as it is for a computer, as it is for a car.
And it feels like this kind of computational thinking is a problem-solving power tool that we should be using in all fields. It seems kind of vital to educate young people to think about the power of data in all subjects. So could computational thinking grow to be part of our biology curriculum or geography syllabus?
100%. I mean, actually, your term there is a great term. It's a problem-solving power tool. I think that's absolutely. I've never actually heard that. I think before. That's a really good characterization of it. I mean, I would even go further. I think it's possibly the most successful single system of problem solving the world has ever had. You wouldn't say it's the only system by no means, but I think it's extreme because it's very specific, covers a wide range of areas. Let me put it another way, we're forcing the world to learn maths for 10 plus years of their life. If that subject isn't applicable in almost all other subjects that they're learning, then why are we forcing it on them as a compulsory long-term subject? So I would almost turn the thing around the other way. Is there a computational subject that in fact is applicable across all these areas, such as biology, history, English, and so forth, that people do? And if not, it's a side subject or a particular vertical subject. So my answer to that is yes, there is such a subject. It's this computer-based maths, if you want to call it that, or computational thinking, incorporating these different aspects we talked about. And absolutely, in real life, it is now increasingly key in virtually every area. There's a kind of a computational biology. There really is a field called computational biology, but there's computational history, there's computational archaeology. Virtually every field has a computational arm to it. Obviously, some have had that for a long time. Physics, for example, has been highly computational for a very long time because it was amenable to computation. And by the way, one of the things governments in particular get wholly confused about is this. The reason that all these fields are now suddenly computational in the real world is because we have high-powered computers that allow us to take this fantastic, this power tool of problem solving, so to speak, and apply it in all of these different areas. We weren't able to do that before computers because, as we were talking about, it worked in physics and accountancy. It didn't work really in biology, too messy. So in a sense, the computer is the enabling factor that has allowed computation to be so central in our lives. In education, we're saying, let's strip that major factor out and then hope we can have contextual problems that mirror the outside world. Well, it can't happen. If you strip out the main machinery that enabled it, it's not going to work. So you've got to have the computer. It's not just an add-on. It's absolutely central to this particular process. And so I think the way school and college should work, we should have a core computational subject, which is what maths is sort of billed as, but isn't. That subject should then be used in all these other subjects as much as possible. And so take the biology. I think biology syllabus is actually a really good case in point where the world is moving forward with computational biology at a rate of knots. And yet our biology syllabus has painfully little of this in. And it can't have it in at the moment because there's no central subject that's helping with this. And so it has a lot of difficulties integrating. And I know that we've been having a lot of discussions with universities in the UK recently because they have a huge problem. They have students, even top students who arrive at top universities with maths qualifications who can't do the most basic thing they want done, let's say in their biology syllabus. And so they have to start off at the beginning of their first term trying to get them up to speed with how to think about computationally, how to do.
So much time is lost.
Huge amounts of time and confidence at the same time.
And all of this kind of leaves me wondering, what would you say are the best and worst case scenarios for education in the future? Say we wake up tomorrow and it's the day of the GCSE maths exams in 20 years' time. What is the best case scenario for you? Does this day exist at all? What is the danger of nothing having changed?
It's a great question. I mean, it's slightly predictive in saying if we woke up with GCSE in 20 years' time, that might be a fairly bad case scenario. So I think a bad scenario is that we go on measuring the wrong things, forcing everyone therefore to learn and also picking out, in a sense, the wrong characteristics that we really don't need, promoting people who are best at those and not people who are better at other characteristics. So I think, and we've had some of that. I mean, I think some of that is happening at the moment and it's quite depressing to watch. And then you get all sorts of weird problems, like you get quotas for things, it's like, well, we've got too many people coming from this category because we haven't measured correctly what they're actually good at and what we care about. And therefore we all think that's very unfair. And so therefore let's decide that we only have, this sort of percentage of these people and that person, where actually the measurement was all wrong. So I think we've got a lot of trouble with turning education into more of a factory with standard components of students coming out, when what we need, as you alluded to earlier, is more creative humans that can leave the factory production to the machines that we've so successfully built.
And one of the interesting things is actually in the UK, when the A-level algorithm went wrong, it gave algorithms kind of a bad name amongst young people, and very few students could talk about how they wished the algorithm could have functioned because they hadn't learned about that at school, but they knew it was unfair. So you do end up with this big gap in understanding. But I say educational, which makes me think of young people. But actually, is computational thinking only for young people to learn? At the moment, are we in a danger of a massive tech gap emerging between those who understand what AI does, how it works, and those who sort of say, well, we have a load of algorithms nowadays, they know everything about me, then my life's easier for it. Is AI a bit of a runaway?
No, there's a huge computational divide out there, and it'll get bigger. And there's no reason why adults can't learn computational thinking better than they are at the moment. In fact, we're starting work on taking some of the computer-based maths curriculum we've been designing at sort of a school level and helping universities with that, and also potentially employers. And actually, there's a lot of interest in that right now. But if you just go back to a case in point, you talk about adult training where it's needed and so forth. Look at the folks who came up with the algorithm that determined people's A-level and GCSE grades. Oh my God. I mean, it's like and I wrote a blog post about this last year, a rather critical blog post. Virtually every mistake that could be made there was made there, in my view. I named this the off-qual Procrustes algorithm. So Procrustes was a guy in Greek mythology who was supposed to have run an inn where he invited people into the inn. And if they were too long for his bed, he chopped their legs off. And if they were too short, he stretched them until they were exactly the right length. And I thought that what they tried to do with schools by saying that basically you had to fit within the, more or less, it was a little bit more sophisticated than this, but you had to fit within the same curve as the previous year's cohort at your school was nuts. And it's exactly the wrong thing. They'd thrown out most of the data. They made it too simplistic. They decided they based it on one monoparadigm approach. And I mean, as I said in this blog post, I think if our folks in the authorities in the UK had proper computational thinking training and they understood computational thinking properly in the ways we've been discussing, it would have been clear some of these mistakes at the outset wouldn't have been made. So as I put it, Ofqual and the like were hoisted by their own petard of lack of computational thinking in the curriculums that they promote. So
is anyone succeeding in implementing this kind of thinking into their curriculums? Are there any countries doing really well at it? And have we seen the outcome of that yet?
The basic answer to that is no, not really. So we started some programs in Estonia, who were the first to kick off with the sort of work we've been doing. And I think Estonia was already, doing relatively well at these sorts of things, though relatively traditional curriculum, but they introduced coding very early and things like that. Look, we've had some progress there. There have been piloting, but it's as with many governmental things, it's slowed a bit more than I would have liked. I think we've got much new interest actually since the pandemic in restarting this. We've been trying to do work in the UK as well. We'd like to have a music exam grade type approach for computational thinking. And because I think as a musician, you'll notice, of course, exams I think for music are quite sensible in many ways. You take the exam mostly when you're ready to take your grade exam. Most people do quite well in it. I don't think the exams have been dumbed down because basically, so you can marry in the sense, the fact that people do quite well in them with the fact that they haven't been dumbed down because there's a grade that you can go forward to in different instruments and so forth. And so I would like to see an approach like that that I think we can initially have in parallel to what's out there, and particularly at university level. I think, getting it into schools, there's so much time pressure in schools. It's very difficult to introduce that. But I mean, that is ideally what I'd like. I think a stepping stone would be to have a sort of computer-based maths A-level as an alternative to traditional maths. But of course, that needs acceptance of universities. And it's hard to get this working because you need enough universities to accept that they want that ahead of having enough people running it, which means they don't have enough experience of the sort of people who come through. So then you're in a sort of catch-22 position.
And as we teach more and more people about data science and about computing and coding, where would you say teaching AI ethics comes into this? Because it's really important that people hold the tech that's being created to account.
Yeah, that's a very good question. Well, you see, I think AI ethics is probably multiple pieces, actually. I mean, there's a piece of history there as to where command and control goes wrong, which actually isn't very different. I mean, the details are different, but it's not that different from authoritarian governments and monopolies, business monopolies that have caused trouble in the past. So I think there's a lot that's actually to do with people's understanding of, I think a good way of justifying why you have history for most people is so they don't repeat the same mistakes of the past. And I think there's a lot to put into history that fits with this AI ethics, which you can learn from the past. I think that what you need to learn perhaps in a core computational curriculum, as I tend to call the future, because I don't want to bias it by its name of maths or not, is you need to learn a lot more about the kinds of things that go wrong with the machinery and where you can trust it and can't trust it. And that, I think, is very central to what people should learn in that core computational curriculum. In the end, that happens with all machinery. And I think the ethics, in a sense, sort of fit with that. I mean, the ethics of where it's reasonable and how fast it's reasonable to drive your car, in a sense, are connected to some extent with the machinery of cars. Not entirely. It's a complicated, and we're seeing that ethics come up now with self-driving cars. That's a key problem. What's the judgment you make as a human if you're going to have an accident with something? And is the computer judgment, is the cold computer judgment right and ethically sound and so forth? So I think it mixes a lot of machinery, and therefore you need to know about the machinery. You need to know about modern machinery, and you need to know where that goes wrong and where it's going in the future. And I think it's a lot of what I would say here is you need experience of the past and of the machinery. I like the word experience because I think and you need experience of as much reality and with all the mess that comes with that as you can have. And the experience is hopefully what gives you some immunization against problems that will come up. And that's kind of where we need to, I think to your earlier question, education needs to build experience as much as possible, accelerate experience. Mm-hmm. And we need to do our best job of doing what we see as the current real life that we need to have the experience of and accelerate that towards. Yeah. And I think this is a very critical problem. I mean, this is of the moment. And if we don't get our act together quickly on this, it will cause the sort of societal problems that we've already actually seen starting to emerge.
I think it's so important to show young people that education is so much more than the sheet of paper they come out with and the set of grades that they have. What advice would you give to those interested in careers in tech and AI?
I think, let me think about it a moment. I think what I would say is, firstly, don't do it because you think it's important to do. Do it because you're excited by some actual aspect of that, and go into the thing you're excited in as much as possible. I mean, you can't always do that. You need to make money in a job, but don't try and chase where the money is. Chase your interest. And I think that's important in all walks of life. And I think it's very important with a bubbling area like AI and tech. It's always very exciting when a new area like this comes up. And you get a certain number of people who rush to the area just because it's new and important to be in that area. But I think actually the people who make the most progress are people who really find some genuine facet of it that they're interested in. And it might be that you're really a biologist, to pick up our early example, and you're really wanting to do biology, but it just turns out that the future of biology is computational biology, and that therefore the facet you should go down is biology and computational biology rather than directly into, I'm going to join tech in its own right.
Definitely find your niche and go with that. And finally, Conrad, if there was one book, album, podcast, article, concept, or hobby that you wanted everyone listening to go and read, listen to, research, try, what would it be?
Oh gosh. Well, I mean, obviously I'm going to plug my own book, but apart from that,
the Maths Fix, everyone.
The Maths Fix, yes. I don't know. I think one just needs to pick something one finds in. I think, self-analysis. Understand what it is you really enjoy and really don't enjoy, and what you've been pushed into by your school, your parents, whatever it is, and try and analyze for yourself as much about yourself as you can. And in a sense, that's not exactly a hobby, but I think it helps you abstract out possible hobbies that you might have in the future. So I'm not sure that's quite the answer you're looking for, but that was the first thing that came to mind.
It makes a lot of sense. I think it's definitely some good advice. Conrad, it's been great to speak with you today. Thank you so much for joining us on the podcast. And I look forward to the 23rd of June, when I'm sure I will be thinking of Wolfram Research and everything that you guys are doing to make such an amazing impact. Thank you.
Great. Well, thanks very much for a really interesting interview with some very different questions than I often get.
We hope you enjoyed this episode of the Teens in AI podcast. If you'd like to find out more about computational thinking and Wolfram Research, we really recommend the resources in the episode description. If you haven't tried using Wolfram Alpha before, do take a look. We promise it will transform the way you research and work forever. To stay updated on the podcast, follow us at Teens and AI Pod on Instagram and Twitter, and do let us know your thoughts on the future of maths education. You can catch new episodes of the podcast every Thursday. Thanks for listening, and I hope you have a great week.